Hi everyone. So in this class, let me discuss some of the definitions and examples. Okay. So the first definition is cluster point, or it may be sometimes called as a limit point of a sequence. Okay. So let me know the meaning of this cluster point. Okay. Sequence. Okay. So here we draw the real number line, that is of the form like this. This is the number line. Okay, here this is the closed interval from -1 to 1. Okay, here I draw x naught, that is x naught is equal to a point. Okay, so this is a smaller interval around x naught, that is open interval x naught minus delta to x naught plus delta. Okay, so here a is the set, so that is closed interval -1 to 1. Okay, so it is the subset of our real line. Okay, so this is the real line, in that this is my closed interval -1 to 1 is the subset of your R. So here I take a point x naught is equal to R. So is x naught is our cluster point of A, cluster point of the set A. So for that we have to check. Okay, so there will be, so here I am drawing open interval, that is x naught minus delta to x naught plus delta. Okay, so between these 2 points, that is from x naught minus delta to x naught plus delta, there are infinitely many points. Okay, so there will be infinitely many elements of A inside this interval, that is open interval minus x naught minus delta to x naught plus delta. So no matter how small delta is, so delta is here, your delta is very small, negligible number. Okay, however your delta is small. Okay, so any open interval around x naught, around this point x naught contains infinitely many elements of A. So x naught is called as your cluster point of the set A. So the meaning of your cluster point is generally, so we take a number line, okay, that is real number line. Okay, so there we take a closed interval -1 to 1. So there I take a midpoint, that is x naught, that is 0. So around your x naught I draw a small interval, that is an open interval, that is x naught minus delta to x naught plus delta. Okay, so any open interval, okay, around x naught, this x naught contains infinitely many elements of your A. So between these 2 points means here your closed interval is A, that contains your point x naught. So around your x naught we can draw infinitely many points, intervals also. So therefore here your x naught is your cluster point. So here we define the definition of your cluster point, that is a real number cluster point or limit point of a sequence. So definition of your cluster point is a real number L is said to be a limit point of a sequence if every neighborhood of L contains infinite number of elements of a given sequence. So here a real number L is said to be limit point of a sequence if every neighborhood of L contains infinitely many elements of the given sequence. So here in this example, so here your closed interval is there. Okay, here I take a midpoint, that is L as 0. So around your L there are infinitely many points, yes or no? So yes, because here around your x naught I draw the points, that is x naught and x naught minus delta and x naught plus delta. Between these 2 points means x naught minus delta and x naught plus delta, we can draw infinitely many points, many elements. Okay, so here also we are defining a real number L is said to be a limit point of the sequence if every neighborhood of L contains infinitely many elements of the given sequence. So in other words, another definition is there, that is a real number L is said to be cluster point of a sequence AN, if given epsilon greater than 0, however small, a positive integer m and a positive integer m, there exists a integer k is greater than m such that ak minus L is less than epsilon. Ak minus L is less than epsilon. So that is, so this is here your L minus epsilon and L plus epsilon lies between your ak. So your L minus epsilon is less than ak is less than L plus epsilon. Thus every neighborhood of L minus epsilon and L plus epsilon of L contains infinitely many terms of the sequence. So if I take here your L as this, so around your L there are infinitely many terms, that is a1, a2, a3, so on an. So on an. So here we are dealing with your real number L is said to be cluster point of the sequence an. If given epsilon greater than 0, there is a positive integer m and k such that ak minus L is less than epsilon. Okay. So for all k greater than m. So your L minus epsilon is less than ak is less than L plus epsilon. So around your means thus every neighborhood of L minus epsilon and L plus epsilon of L contains infinitely many terms. With example, let we discuss this. Okay. So the sequence. So this is the sequence 1 by n. Okay. So here 1 by 2, 1 by 3, 1 so on. Okay. So these are so on. So if your n tends to infinity, then it is just to 0. Okay. So means so this is the sequence. Okay. Decreasing sequence. So here your term reaching towards 0. So around 0 there are infinitely many terms. So if I take here, if I write here 0, so around 0 your 1 is there, 1 by 2 is there, 1 by 3 is there, means all the terms are there around your 0. Okay. If your n tends to infinity, means this sequence has only one limit, that is 0. So therefore the sequence 1 by n has only 0 as its limit point. So here the sequence that is n cube. So here I write, so if I put n is equal to 1 cube 1, 2 cube 8, 3 cube 27, 4 cube 64. Okay. So this is of the form increasing order. So here we can't say all the numbers, means all the points around one exact point. So because it is in the order of increasing order, so it is reaching towards your plus infinity. Therefore I can say this has no limit point, because this is divergent sequence. So another example is, so this is the sequence 1 plus minus 1 to the power n. So if your n is even, it is 0, it is 2. If your n is odd, then it will become 0. So here when your n is even, you get 2. When your n is odd, you get 0. So here you get two limit points, those are 0 and 2. So therefore this sequence has two limit points which are countable in number, but now the range of the sequence is 0 and 2, which has no limit points. So here we have to find only one limit point to satisfy your limit of a sequence definition. Only one limit point should be there, but here we are getting two limit points. Therefore because of that reason this sequence has no limit points. Okay. So according to your definition, so a real number L is said to be limit point of the sequence if every neighborhood of L contains infinitely many terms of the sequence. Okay. So this is the definition of your cluster point or limit point of a sequence. So based on that I have given two examples. So several times in your question paper this definition and examples have been asked. Define limit point of a sequence or cluster point of a sequence and give an example. So lots of time this question have been arised in your previous year examinations. So clearly see the definition and note down the example also. So next concept is your limit superior and limit inferior of a sequence. Limit superior and limit inferior of a sequence. So here I am taking, let an be a bounded sequence, then the sequence has least and greatest limit points. Okay. If your sequence is bounded, one is greatest point, another one is least point. Here we get. Okay, so the least limit point of the sequence an is called limit inferior of a sequence an. The least limit point of the sequence an is called limit inferior of an and is denoted by limit infimum of an as n tends to infinity, or limit infimum of n tends to infinity as limit infimum of an as n tends to infinity. So another thing is the greatest limit point of the sequence an is called your limit superior of an, limit superior of the sequence an, and is denoted by limit supremum of an as n tends to infinity, or this is denoted as limit supremum of an as n tends to infinity. So these are the two definitions. So and for this an example is for the sequence an defined by -1 to the power n for all n belongs to n, the only limit points are, so here the only limit points are for this sequence -1 and 1. Okay, so whenever n is even you get 1 and n is odd when you get -1. So the set of limit points are here -1 and 1 which is bounded. Okay, which is bounded means it is lying between -1 and 1 your sequence an. So therefore here limit infimum of an as n tends to infinity is -1 and limit supremum of an as n tends to infinity is 1. So here you are getting limit infimum of an as -1 and limit supremum of an as 1. So this is the example for your definition. So another example. So here I am taking for the sequence an defined by an is equal to 1 by n for all n. So here the only limit point is 0. Okay, the set of limit points for this sequence is 0 which is bounded. Therefore here limit infimum of an as n tends to infinity, so this is equal to limit supremum of an as n tends to infinity as 0. So for both the infimum and limit infimum of an and limit supremum of an, here you get limit inferior and superior of a sequence an is 0. Of a sequence is 0. So for the constant sequence an is equal to k, so here also limit infimum of an and limit supremum of an is k. So because constant sequence, if an is equal to 1, so here you get limit infimum as well as limit supremum of a sequence is 1. Okay, so in the similar manner for the sequence n is equal to -1 to the power n for all n belongs to n, here the limit infimum of n is -infinity because you are n tends to infinity. Okay, this here you get -infinity. So therefore limit infimum of n is -infinity because if when your n is odd, so when your n is even, so you get +infinity because -1 to the power 2. Okay, as n tends to infinity it will become +1 into infinity as +infinity. So these are the examples for your limit superior and limit inferior of a sequence. And this question also came several times even in your previous year examinations, that is define limit superior and limit inferior of a sequence and give an example. So you write down the definition and give a simple example for your definition. Okay, so this is also important for your point of examination. So you read it carefully. So next example, give an examples of a sequence having no cluster point, one cluster point, two cluster points, infinitely many cluster points. So here the sequence n has no cluster point because your n is reaching towards infinity. Because of that here we can't define your cluster point, that is limit point of a sequence, because when your n tends to infinity is reaches towards infinity and this is of the order increasing order. So therefore here we can't exactly say what is your cluster point. Because of that reason the sequence an has no cluster point. The sequence 1 by n has one cluster point. You know that when your n tends to infinity it reaches towards 0 and all the values of your all the values means all the values of this sequence is around 0. Therefore here it has only one cluster point, that is 0. And another example is -1 to the power 1 has two cluster points. When your n is odd it is -1 and when your n is even it is 1. So fourth example is the sequence 2, 1 plus 1 by 2, 2 plus 1 by 2, 1 plus 1 by 3, 2 plus 1 by 3 has infinitely many cluster points, because here we can't say exactly what is means finitely exactly this is the cluster point means in a finite set we can't say, because here different cluster points are there, therefore it is the it has infinitely many cluster points, because every natural number is a cluster point, So here there are some examples. Find the cluster point of the following sequences. So minus 1 to the power n, 5, minus 1 to the power n divided by n, minus 1 to the power n into 1 plus 1 divided by n, 1 plus 1 divided by n to the power n plus 1, 1 plus 1 divided by 1 factorial, 2 factorial, plus 1, 1 divided by n factorial. So here first example, that is an is equal to minus 1 to the power n. So here when your n is odd you get minus 1, and when your n is even you get 1. Therefore the sequence an has two cluster points, namely minus 1 and 1. So this is the sequence. So here n is equal to 5 is a constant sequence converging to 5. Therefore the sequence an has one cluster point, that is 5. So another example, that is n is equal to minus 1 to the power n divided by n. When n is odd, minus 1 by n. When n is even, 1 by n. Therefore limit n tends to infinity, n is equal to 0 for both the cases. So that the sequence n converges to 0. Therefore the sequence n has only one cluster point, that is 0. So left examples are homework for you. So you try to solve all the examples. Okay. Next, find the limit superior and limit inferior of each of the following. So here first example is 1, 3, 5, 1, 3, 5, 1, 3, 5, 1, 5, 7, 19, 1, 5, 17, 19, 1, 5, 17, 19. And another example is n is equal to minus 2 to the power minus n into 1 plus 1 divided by n. And fourth example is n is equal to minus 10 to the power minus n into 1 plus 1 divided by n to the power 2. So for first example, that is 1, 3, 5, here n is equal to 1 when your n is equal to 3 minus 2. So when your m is equal to 1, it will become 1. So this is 3 when your n is equal to 3m minus 1. When your m is equal to, here if I put 1, if I put 3m minus 3m, so this is exactly 3m, this is 3m plus 2. Okay, so when you are here m is equal to 1, it will become 3. When you are m is equal to, in this case, when your m is equal to 1, then it will become 5. Then it will become 5. So therefore the set of cluster points of your sequence an is 1, 3, 5. So here limit supremum of an is equal to maximum of 1, 3, 5. So when there are your an equals 1, 3, 5, set 1, 3, 5. So maximum of 1, 3, 5 is 5. So here your limit supremum of an is what? 5. So this is the standard result, and this is also a theorem also there. So when limit n tends to infinity, an is equal to maximum of a1, a2, a3, an, then maximum of that value can be written, and limit infimum of an as n tends to infinity, minimum of these three values, that is 1. So next another example, second example is homework for you. So there 1, 5, 17 and 19 is there. 1, 5, 17 and 19 is there. So here your limit supremum of an is maximum of 1, 5, 17 and 19, that is 19, and infimum of limit infimum of an is minimum of 1, 5, 17 and 19. Therefore there we can say minimum of 1, 5, 17, 19 is 1. So next example, third example is here an is equal to minus 2 to the power minus n into 1 plus 1 divided by n. Therefore limit n tends to infinity a n is equal to limit n tends to infinity minus 2 to the power minus n into 1 plus 1 divided by n. So this can be written as limit n tends to infinity 1 divided by minus 2 to the power n into 1 plus 1 divided by n. So when your n tends to infinity, it becomes 1 divided by 0 is 0, 1 divided by infinity is 0 into this value 1. So this is equal to 0. Therefore the sequence n converges to 0. That implies that the set of cluster points of n is 0. So therefore limit n tends to infinity means limit supremum of an as n tends to infinity and limit infimum of an as n tends to infinity is 0. For both the cases here we are getting the cluster point as 0. Therefore 0 is the limit infimum and limit supremum of the sequence an is equal to minus 2 to the power minus n into 1 plus 1 divided by n. So with this I conclude this class. So if you have any doubts regarding limit infimum, limit supremum of a sequence and limit of a sequence, then you can send questions to my WhatsApp number so I can solve your problem. Thank you.